Alright, so let's talk about some examples. We're going to look at one very simple example, and from that example, we are going to look at the trade-off between bias and variance. So the example is the following. Let's consider a sine function that I'm drawing you here. And the sine function, of course, is a sinusoidal shape. And then from there, I'm going to give you two data points, data point 1 and data point 2. Okay, so this is the data point. And then you have two training data points. And then these two training data points, they are sampled uniformly in the interval of -1 and 1. And so let's call them two coordinates, x1, y1, and x2, y2. The hypothesis set 0, I define it as M0. That would be the set of all the lines that is constant. And I'm going to define the hypothesis set 2, that is the set of all the lines. So what we are going to do is the following. I'm going to give you two data points that comes out from this sine curve. And then I want to fit these two data points using two different models. The first model is an extremely simple model. It says that I'm going to find you a straight line and then try to fit these two data points. The second hypothesis, which is the second type of lines, is that I'm going to find a line that has a slope to fit the two data points. And we want to ask which one is a better fit to this problem. So now, without doing anything, when you look at this problem, you will start to think that a hypothesis set 0 is a straight line. That is an extremely simple model. And then the other one is the first order line. That seems to be a little bit more expressive. So I'm inclined to think that maybe the first order model would be a better one than the 0 order model. So let's look at whether this intuition is actually correct. So we want to find which one can fit these two data points better. In other words, in addition, which one will be able to generalize better for this problem. So if you try to draw a straight line and try to draw a first order line for these two data points, you can see that if you give me any two data points, I can tell you a fitted line. Okay, so for M0, for the first hypothesis, I'm going to give you this equation. That's fairly easy to calculate. This is y1 and y2. I just calculate the midpoint and then I draw a line. That will be that equation. That would be my hypothesis. For M1, the equation is here, right? So now you have two data points. Okay, so you have these two data points. And then how can you do that? Well, you need to look at the slope. You also need to look at the y-axis, y-intercept. And by doing some very simple calculation, algebra, then you can show that hx is given by this equation, where you have the slope given by y2 minus y1 divided by x2 minus x1 times the x plus the y-intercept. Okay? So now when you look at this diagram, you see that, hey, once you give me these two data points, I can pretty much fit very well using the first order line compared to the 0th order line that's leaving a lot of space. So now let's try to calculate the outsample error, because in sample error we understand from the previous slide that this first order equation is a very good fit. So let's look at the outsample error. So suppose you look at the first order equation, then you can get this. The outsample error, if you find a line, it would be this. It would be 0.2. Now, how do we calculate that? So suppose I draw you a sine function, okay? And then I tell you infinitely many training samples, okay? And then now you draw a sine function. Then you ask, well, I want to use a first order line trying to fit this sine function. This is the ultimate generalization error that you can ever get, right? Because I know the underlying true sign function, and then I want to find I will go to my hypothesis set. I find the best possible line that can fit this the sign function, and I can do that by using some very simple calculation, and you can show that the outsample error is 0.2. That can be done without looking at the training set. Okay, so that can be just purely done by looking at the geometry of this problem, and then you can calculate this 0.2. And we can also do the same exercise for the zeroth order calculation, and then you can see that the zeroth order calculation says that you can only find a horizontal line that can fit this data set, and so since you have a sine curve, then that means you can calculate the error that will be 0.5. You can also do that. Alright, so now let's go into the scenario where you have training sets. Okay, so now the training set, let's recall, you only have 2 data points, and then from these 2 data points, you are going to shuffle these 2 data points randomly because you're drawing a different training set from the population. So now, for every pair of data points that you're drawing from your training set, for every training set that you have, you will be able to draw a horizontal line. Okay, for different training sets, you will be able to draw a different horizontal line. Now, of course, in the middle, because you're taking the y1 and y2 divided by 2, taking the midpoint, what we expect to see will be the following. You will have more samples that are concentrated in the middle, and you have fewer sample curves that are sitting at the top and at the bottom. So these will be all the possible trajectories of your hypotheses. All the hypotheses, they're horizontal lines, but then by drawing different training sets, you will have different horizontal lines. There are more chances that you will hit in the middle, and then there are less chances that you will hit at the bottom and at the top. Now, if I try to draw the average hypothesis, which would be the average of all these gray lines, then I will be able to draw you the red line showing you here. This is called a G-bar. In addition, I will be able to also draw you the variance that show you a band such that all these gray lines, they will have one standard deviation within the band. So that will be the average bias, that will be the average, that will be the standard deviation. Okay, now you do the same thing for the first order equation. Okay, so you also draw a 2 data points, and then because you're drawing 2 data points, you're trying to fit these 2 data points very, very well using a line with a slope. So you can fit that. Now you draw all these lines on the curve, and now suddenly you see a very surprising phenomenon that all these curves, all these lines, you have lines here, you have lines there, you have lines in the middle, you have lines somewhere else. You can also try to calculate the average of all these gray lines, and you can show that the average will just be the red line I'm showing you here. That is the curve that we showed you 2 slides before, which is giving you a very, very good generalization error. However, let's also try to plot the standard deviation of all these curves. Okay, so you make all these curves together, and then you can show that all the standard deviation will create a band. It's a very, very big gray area. So what it means is that, yes, your red curve, it seems to fit better to the blue curve. However, you have a big variance over there. Now, in fact, if you try to calculate, you will be able to get infinitely many training data sets, and then you have 2 quantities. You will have the red curve, and you also have the variance of the X. Now, in these 2 examples, you can see that the bias of the first example is 0.5, and then the variance is 0.25. Now, this is not a very, very good model, but you can achieve these 2 numbers. Compared to the other case, yes, your bias is significantly lower. This is 0.21. However, your variance is actually 1.69. Now, if you add the two numbers up, this case would be significantly worse than the other case. So what has gone wrong? Well, what has gone wrong is the following. You look at the second case here. Yes, you have your bias, your distance from your red curve to the blue curve is very, very small. Okay, that is known. Okay, so the bias is small. However, your variance changes a lot because for every 2 points, you will just fit at that particular instant. You're not able to understand what will happen over when you have more data points. The problem comes into the situation because you have finite number of training samples. If the number of training samples grows, then of course, this linear model will become a better one than the zeroth order model. And therefore, this gives you an idea that the number of training samples should somehow be related to the model complexity that you're choosing. So this slide summarizes what's happening here, that G bar is a very, very good average, but your error bar, your variance is very, very big. And so what it corresponds to is that you can think of you have a very, very powerful canon, but then it's not accurate. And therefore, ultimately, when you try to calculate the generalization error, that is not a very good generalization. So I want to draw your attention to this slide by understanding the difference between the VC analysis and also the bias and variance analysis. In the VC analysis, we have this curve of the number of training samples. Okay, so as the number of training samples goes up, your in-sample error should also go up. Okay, why? Because as you have more sample data points, it's harder and harder for your model to fit all the training samples, and therefore your in-sample error will grow up. Now, the out-sample error will go down because the more and more training samples you have, then the better and better generalization you will be able to achieve. There are 2 points on this curve. The first point is here. This is the in-sample error. Okay, so this gap is measuring how far you are from 0 to the point that you can train. Now, then this gap will be the outsample error, and then the difference between will be what we call the generalization error. So VC dimension is trying to capture the generalization error by looking at the E in and E out. Now, how about the bias and variance? The bias and variance is doing a different thing. The bias and variance you also have the same curve. However, the bias says that I'm going to measure from 0 to that's a curve called the average curve. Okay, so if you look at the diagram here, so you have this black line, that is the average curve. Okay, that average curve is calculating by using all the training sets, and you take the average. That is ultimately what will happen when you have infinitely many different training sets. That's the black curve that defines the bias. And then from the bias to the outsample error, there will be a fluctuation that is called the variance. Okay, and therefore the outsample error will become the sum of the bias and also the variance. Now you can see that the VC analysis and also the bias and variance analysis, they're actually trying to achieve the same goal of trying to calculate the outsample error. However, they're doing 2 different approaches. So to summarize, what is the difference between the VC analysis and also the bias and variance analysis? Well, in VC analysis, the thing that you're using is independent of the learning algorithm A. So for whatever learning algorithm A you choose, because it doesn't depend on the learning algorithm A, because you're using the Huffington inequality that's universal for all A's, VC analysis is just immune, it's agnostic to the particular learning algorithm. Bias and variance, on the other hand, depends on your learning algorithm A. In other words, if you choose a different learning algorithm, you will end up having a different result, and then that will give you a different bias and variance trade-off. So with the same hypothesis set, VC analysis always return you the same generalization bound because that's the universal bound according to halving inequality. That's guaranteed over all possible choices of the data set. However, the bias and variance for the same hypothesis set, you can have different final hypothesis G of D, and that depends on the final hypothesis, that depends on the training set that you're using, and therefore you have a different E out for different data sets. And therefore we need to take the expectation of the E out in the bias and variance case. Now, in practice, you may ask, whether VC dimension or bias and variance is more preferred to analyze. The answer is that both they have limitations. For VC analysis, calculating the VC dimension could be one difficulty. And in VC dimension, we also understand that the VC dimension itself, the VC analysis itself, the generalization bound itself, it is not a very, very tight bound. And so the estimate that you provide is not a very, very accurate estimate. The bias and variance problem is that the bias and variance you just cannot calculate. Why? Because in order to calculate the bias and variance, you need to first know the target function. And since you don't know the target function, there's no way for you to calculate the bias. And similarly, you have no way of calculating the variance. Since you do not have the F, bias and variance cannot be calculated. This kind of notion is not able to give you a practical algorithm when you're trying to design a machine learning method. Okay, so the take-home message here is that bias and variance, they are very, very useful tools for you to understand the fundamental limitation of your learning scenario. It tells you that fundamentally what you care about would be going from your particular sample, your particular hypothesis to the average. That is measuring the variance, and then going from your average to the target that is measuring the bias. And it has to be sum of these two that quantify the generalization error. Okay, so that concept is useful when you try to analyze different learning models. So for example, if you have an extremely complex learning model, then what do you expect? Well, if you use a very, very complex learning model, then you should expect to see that the variance will grow. Okay, because when you have a complex model, then the bias will be small because you will be able to fit better to your data points. So the bias will be small. However, the variance will grow because for the finite number of training sets, then the fluctuation over different training sets, that will change your final hypothesis significantly. And therefore, you have a big variance that will create a trade-off between the two. Okay, so sample complexity and model complexity is also present in the bias and variance analysis. Okay, so bias and variance analysis is very popular in the literature. So I encourage you to take a look at these references, including the first one that's from the Learning from Data textbook, and also there are a couple discussions in the two other textbooks that is listed in our website. And then here you have 3 additional lectures by different other universities. They also talk about this bias and variance concept.